Cool. Hello, guys. Oh, why have we got Teams up? That's weird. Uh, Very weird. Yeah, cool. Could you guys comment your names when you're here? Um, that's better, isn't it? Cool. All right, let's do a quick register. Yeah, I decided to wear a green t-shirt today, which was it was a bit of an oversight because now I'm a floating head. But all right. So all right, Harry. So you're here instead of later. That's fine. Jasmine, Molly. Okay, Sally's here as well. Fine. Melissa, Jack, Grace, Ollie. Anybody else out there? So Ed, Elizabeth, Dan, Poppy, Jolie, Jake, Emerald, Rob, Dom. Missing all you guys. Hello, can I watch the story? It's my birthday today. Uh, Happy birthday, Emerald. Hey, Emerald. Cool. Let's get started. If anybody else shows up, they can comment in a minute. All right. So yeah, we're gonna start. Well, today we're gonna continue where we left off yesterday. Um, can't believe I wore a green t-shirt. Such a good idea. Okay, so we're going to be looking at. Oh, and Jake's here as well. Cool. Just take that off. Okay. So yeah, continuing what we did yesterday. So I think we did. If you guys might have to remind me because I did teach this twice on Wednesday. I believe we did this question. I believe we did this question. Then I don't think we did this question. So this is this one. Cool. Right, so we'll continue doing what we did on Wednesday. So this is worth 6, 7, 8, 9, 10, 11 marks. I'm gonna give you guys 11 minutes to try it. Comment in the chat if you need help, and well, then we'll go through it in 11 minutes time. So let's put my timer on. Bang, bang, bang. Start a timer. There's the timer. You can't see anything now, so let's fix that. There you go. Cool. Yeah. If you guys want to give it a go, and let's see if there's any tricks to it. So it's a binomial model. Oh, and then it turns into a. Yeah, it looks a bit tricky, Patsy, but give it a go. Sorry, Rob, I didn't see you. You didn't comment, so how am I supposed to know? You are present now, though. Cool. Right, so 10 and a half minutes to see how you guys get on with this. Not sure of the problem. The question is really blurry to the point I can't read it. Anybody else got blurry question? Nice and crisp for you. Brilliant. Sorry, Jasmine. You could try. Yeah, it doesn't look great on my stream here, actually. You could try changing the settings. Um, yeah. My stream health is not bad though today, so yeah. See how it goes. Yeah, do ask if you need help, guys. There's a few tricks to part C. So we need to write out probability distribution. How are we getting on? Anyone need any help? Cool. Right. Yeah, great. So I imagine that people would find part D quite difficult. I'll go through that now. Elizabeth, I'll take you off now. Cool. Okie dokie. Okay. So I'm gonna zoom in because that's quite small, and we'll just go for it bit by bit. Ideal. Cool. Okay. So we're gonna start with what are we looking at? Cool. So, people throwing a data target. Two assumptions. So we need two of the three assumptions we make for a binomial distribution. So we got probability is fixed or constant. So fixed chance of success or fixed probability. No, say probability. Fixed probability. Throws are independent and fixed number of throws. So those are your key points for part one, and all that's worth 1 mark. No, it's not. It's worth 2, but it doesn't say. Okay, part B, using Peter's model, find the probability h is greater than 4. Okay, so now we're actually doing a binomial distribution. So let's write this out. H is a binomial distribution with number of rows 10, probability success 0.1. We're trying to find the probability h is greater than or equal to 4. So if I bring up the trusty calculator, I was wondering what this corner's doing. There we go. Okay, yeah, so bring up the calc and we're going to go to binomial and statistics. So statistics mode, distribution, binomial, BCD. So our lower is going to be, what do you want, greater than or equal to 4. So lower is going to be 4. Upper is going to be 10 because that's the number of trials we've got. number of trials is 10, and the probability 0.1. Cool. If we calculate that, we get, this is why it's worth 1 mark, 0.0128. Cool. All right, part C then. Let's move things up. Okay. So for each child, the random variable f represents the number of the throw on which the dart first hits the target. So there are 8. No, there's not. There's 10 throws for each child. So we're going to draw a probability distribution for this. Definitely going to run out of room, so let's make it smaller than that. So we got x. We've got x. We've got the probability x equals x. And we've got throw 1, throw 2, 3, 4, 5, 6, 7, 8, 9, 10. And we want to find all these probabilities. If we fill in all these probabilities, let's just hide this a second. Cool. So we want to find the probability f equals, I should probably have used f there. Cool, there we go. Okay, so for these probabilities then, the probability of hitting it on the first throw, no, that still doesn't make sense. F is the number. So number of throw, we'll put n, f. Probability f equals n. Cool. Okay, so what's the probability that the child hits the target on the first turn? So we want to find the probability that do we know that? This is the tough one. We don't even need this. Is okay. Ignore what I'm doing. It's much easier than that. All right. If we want to hit it on the first term, we're just kind of doing a standard binomial distribution. So we need it to be. Let's get rid of that. Sorry. Okay, we want to find the probability that the first time that the child hits the target is on the 5th throw. So for it to be on the 5th throw, that you have to miss it the first 4 times and hit it the 5th time. So we're going to get probability of a miss is 0.9 to the power 4 times by 0.1. So in other words, we're doing miss to the power 4 and then hit. Now, the reason we don't need to use NCR is because NCR is when the order can be any order. We need it to be miss, 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 followed by hit. And the first time they hit, that kind of stops the rest of the sequence. So it needs to be miss to the power 4 and then times it by hit. So if you work those out, times it all out, you should get 0.0656. Can't write it there though. No. 0.0656. Okay, so that's the easy bits of the question, and I was trying to overcomplicate there. Okay, so I think we're changing now. So if I get rid of all this. Cool. Okay, so Thomas assumes in the experiment no child will need to hit more than 10 throws for it to hit the first time. Cool. So no more than 10 throws. He thinks the children will all hit the target in their first 10 throws. So he models it as this. Okay, so we've got a distribution. So now we need to draw out the probability distribution. So first throw, second throw, third throw, fourth, fifth, sixth, seventh, eighth, ninth, 10. And our probability is given by this distribution function. So the probability of the first throw is going to be 0.01 plus n minus 1. Well, n is 1, so 1 minus 1 is 0, so we just get 0.01. Probability for the second term will be 0.01 plus 1a, or plus alpha, so 0.01 plus alpha. The next one is going to be 0.01 plus 2 alpha, and that's going to go so on and so forth until we get to 0.01 plus 9 alpha. So we can see this is an arithmetic series every time we are adding on alpha. So if we find the sum of the n terms, sum of 10 terms in this arithmetic series, the sum of those terms should go to 1 because the sum of all the probabilities has to equal 1. So we're going to use the arithmetic sum equation. Sn equals half yeah, 2a plus n minus 1 d. So we get the sum of the 10 terms is going to be half 2 lots of 0.01. There's no space anymore today. Let's get rid of all this again. So sum of the 10 terms, S10 is half 2a, so 2 lots of 0.01, plus n minus 1. N minus 1, n is 10, so 9 times the common difference, which is alpha. Cool. Oh, that should be n over 2, isn't it? So that should be 10 over 2. Cool. Right, so if I work this out, we're going to get 5 lots of 0.02 plus 9 alpha. Can't write alpha because there's no space. Plus 9 alpha. And we know the sum of those has to equal 1. So 1 has to equal 5 lots of 0.02 plus 9 alpha. 5 lots of 0.02 is going to be, so 1 equals 0.1 plus 45 alpha. So 0.9 is 45 alpha. We can divide that to find alpha is 0.02. Cool. Okay, so we found the value of alpha. We now want to try and find the probability that f equals 5, which is that term. So f equals 5 will be 0.01 plus 4 alpha. We know alpha is 0.02, so 0.01 plus 0.08 gives us 0.09. That one. Okay, explain how the models differ in describing the probability a dot hits the target in this experiment. Well, let's have a look. So if I zoom back out. Okay, so the main difference here then is in the probabilities. So Peter had a binomial distribution, and one of the things we assumed that we wrote down in part A was that the probability is constant. So Peter assumes constant probability. Whereas Thomas assumes that the probability is 0.01, so not very likely, but every time you throw, your probability increases. So Thomas thinks each throw. I can't write today. Each throw improves is what I'm trying to write down there, but I can't. Cool. So yeah, so one for hers the probability is constant. For Thomas's the probability improves with each throw. Cool. Right, so that's that one. So it's not too bad, but it's the whole kind of putting it into a table and spotting it's an arithmetic sequence or series, really, as we were looking. All right. Next one. Could you guys try this one? Can you see that? Just about. But we need to make this a bit more visible. Yeah, so that just about fits. If you do want me to make it bigger, just say, I'm just trying to see how it looks on YouTube. Yeah, that'll be alright. So this is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is a 13 mark question, but it doesn't look that difficult. It's kind of like the easier bits of stats, maybe the more boring bits of stats, but definitely the easy bits of stats. So this is stuff that you won't have done since last year. So let's see how you do with it. Most of this is going to be recalling things. So I'll give you guys 13 minutes to do this, which is quite a long time. So please ask if you get stuck or if you need any hints. I need to make it smaller here as well, don't I? 2 seconds. Let's just resize this. Is that visible? Yeah, cool. Right, so 12.5 minutes. Comment if you need any help. Cool. Yeah, Ed, that's all right. I'll have to mark you down as late though, but thanks for coming. Elizabeth, part G. How to explain it? I know the meaning of quartile change. What does it say? So you drew the box plot again, only had to change two values. Okay. Your mean, however, wouldn't be on a box plot. Um, Sorry, I haven't read this one through yet. So there's 40 workers done, and they've had to change two of these values. Um, yeah. So yeah, the median and you think the upper quartile. So going from 75, which was quite a high value, to 35, which is in the middle of the data. So no, that's not going to affect the lower quartile. That'll still be where it is. Okay, yeah, and neither's that. Okay, yeah, cool. So yeah, the median and the upper quartile. Um, so all you need to do is explain which two. So you need to choose the two values, and then say what's going to happen to them as well. Yeah, you don't need to write lots. You just need to explain why. Just kind of like I just said to you then. So where are those points ending up? What things will that affect? Cool. You guys ready to go through this? Okay, so Charlie studying time, blah 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 blah. State the sampling method he used. Okay, so this kind of sampling is convenience or opportunity sampling is what we called it. He stands by the door and just asks people. So opportunity. State briefly and describe an alternative method of non-random sampling he could have used to obtain a sample of 40 workers. So we could use the only other method of non-random is quota sampling. And he wants 40 workers. So he could ask, I don't know, describing it, quota sampling. Well, we don't really know anything about the quota, so I guess you could choose any. My mic was up. Sorry. Yeah, opportunity for the first one, quota for the next bit. Um, to describe it, he'd have to choose a quota. He could use it on like age maybe. So split the 40 workers into age categories, and I take 5 from each category as they walk in. Something like that would do. Okay, Taruni decided to ask every member of the company the time it takes them to travel to the office. So she asked all of them, so she did a census. Okay, cool. So that's all the wordy stuff. Let's get rid of all that and zoom in on the rest of this question. Okay, so here's the results in this box plot. Write down the interquartile range for this data. So we're looking for this range here, which looks like it goes from 22 for 26 to 58. So interquartile range, I would say there is going to be what 30, 32 for that one. We ought to be using units, so it is in minutes, so we should say 32 mins because there's that one mark in this paper, the way units are important. Calculate the mean and standard deviation. Cool, well they've given us these statistics there. So for the mean, remember it's sum of x over n, so that's going to be 4133 over 95, which gives me a mean of 43.5 minutes. For the standard deviation, remember that's the square root of sum of x squared over n minus the sum of x over n all squared. So it's got a message. Cool. So that's going to be 202,294 over 95 minus 4133 over 95 squared, all square rooted, which gives you 15.4 mins. The units are minutes for all of this. Okay, cool. State whether you'd recommend using the mean and standard deviation or the median interquartile range to describe this data. So the data has extreme values. And when you've got extreme values, it's best to use the interquartile range and the median because they are unaffected by extreme values. If you've got the mean, if you've got an extreme value in there, that's going to pull up the mean. It's going to stretch out the standard deviation. But as you can see on the box plot, those values won't actually affect the median or the interquartile range. So Q2 and IQ are unaffected by extremes. Cool. Right. Next bit. So this is a little bit difficult. We have to really understand how these diagrams are made. So, right, we've got two employees, and their journeys to work change. So one of them was at 75, so there's 1 point there, has now moved to 35. It's moved to there. So this point here is going there. And we've got another point which was 60, has now moved to 33. So this point's moving there. So let's have a think about what's going to change. Well, remember the lower quartile means there's 25% of the data below it. That's not going to change because we've got data from above it moving to still above it, so the lower quartiles can stay where it is. The lowest value of the data there is going to be unchanged as well because we haven't changed the lowest value. We also haven't changed the highest value. That's still the same, and the outliers are still the same as well. So the only things that could have changed is our median, and it will have changed because we've taken two values above the median and placed them below it. So that will alter things considerably. It will probably move the median to the left. And the upper quartile is now going to have to move as well because we put more data below it, so the upper quartile is going to stretch towards the mean. So which two values will she have changed? So it changed the median, which will be lower, and the upper quartile. Well, there'll be less data above it, so that will be lower as well. So both of these will be made lower. They'll be pulled down because there'll be more data below them. Cool. Right. Next one then. So I feel like we might have done this one before, but it's been a while and it's quite a hard question. So can you guys try this one? This is normal distribution, but I think it might also have some binomial chucked in as well. And we got normal hypothesis test at the end. So we got 10. It's a 14-mark question. I'll give you guys 14 minutes and see how you get on with it. Comment if you need help. Yeah, that's fine. If send it over now, Elizabeth, that will be all right. It's actually a really good idea for any of you. If any of you want me to check your workings while you're doing this stuff, just ping it over on Teams and I can read through it and give you some comments while everyone else is doing the question. Cool, yeah, Elizabeth. Your workings are spot on for a single battery. You've got 4 batteries, so um, that's the probability of a battery not working. But you've got to now do that to the power 4 because you've got, if one of those 4 batteries goes wrong, her calculator stops. Because it says it'll stop working when any one battery reaches the end of its lifetime. So yeah, do that to power 4 and then you've done it. So nice. Just realised my mic was off. Sorry. Okay. So yeah, we'll start going through it. I've written out the distribution. So L is a normal distribution with a mean of 18 and a variance of about 4 squared. Okay, this bit's kind of key. So it requires 4 batteries and will stop working when any one battery reaches the end of its lifetime. Find the probability that a random battery will last for longer than 16 hours. So we just want probability L is greater than 16. So bring up the calculator. Distribution, normal distribution, NCD. Lower is 16. Upper, big number. Sigma for mu 18. Go. So we get 0.691. There we go. Cool. Next bit. So at the start of her exams, she put 4 new batteries in the calculator. She used the calculator for 16 hours, but has another 4 hours of exams to set. Find the probability her calculator will stop working for her remaining exams. Okay. So what this is really asking, this is a conditional probability question, and it's kind of hard to spot that. But what this is asking us for is the probability L will be for probability that the battery lifetime will last for more than 20, given, this is the key part, that it's already lasted more than 16. So L greater than 20 given L greater than 16. And that's what makes this one tricky. So we're going to use the A given B equation. Hopefully you guys remember A given B is A and B over B. So we're going to apply this. You can't really see that. Move it on down. There you go. So we're going to apply that to the red equation. So we're going to get greater than 20 and greater than 16. Well, if it's greater than 20, it's going to be greater than 16. So we can just, instead of using A and B on the top, we can say, well, the conditions are satisfied by just having it greater than 20. So that's going to be probability L is more than 20 divided by B. Well, run out of room again. Probability L is greater than 20 over the probability L is greater than 16. So that's what we're trying to find for this one. Now we know the denominator 0.691. The numerator we're going to have to work out using the calculator again. So if I go back to the calculator, everything's the same, but we're trying to find the probability that it's greater than 20. And we get 0.308 or 309. So 0.309. I can then write in the top of my equation here, and we can work out what that is. And that should give me, hang on, 0.309 divided by, that should give me 0.447, I think. That one, assuming I've made no mistakes. Yeah, 447. Okay, however, that is the probability of a single battery lasting for more than 20 hours, given it's lasted more than 16 hours. She has 4 batteries in her calculator, and if any one of them goes, the calculator breaks, so we need to do that to the power 4. So we need to do 0.447 to the power 4, which gives us 0.0, basically 0.04, 0.04 for me. I did a bit of rounding there, so yeah, something close to about 4%. Cool, hopefully you're all okay with that. So I'm going to clear some space here. Okay, so All right. So she only has two batteries. So after the first 16 hours of exams, although it's still working, she selects two batteries and replaces them. Okay. So to be nice and confusing, the probability that her calculator will not stop working for the remainder of the exam is 0.199. So we need to work out. Basically, we've got two of those batteries we just worked out. So we're going to have 0.447 to the power 2 times by the probability the two new batteries will last for longer than 4 hours. So times by the probability was greater than 4 squared, basically there. So we'll get the calculator back up to work out greater than 4. This seems like a horrible question, but it's not that bad. All you need to do is keep changing the lower bound of your distribution. So we get a really good probability there. We get 0.9997. Whatever. So if I square those both and times them together, so 0.447 squared times by 0.99977 squared, we get 0.1997 as the probability that her calculator will stop working. Will not stop working. Yeah, so yeah, we've done that. 2 3 sig figs. Mine rounds up more, but I think it's because my first answer I over rounded it. So yeah, it's fine. Okay. Now we've got the hypothesis test. So that was a nice interesting kind of question there about probabilities. But now we've got to do hypothesis testing. So okay, so she believed the lifetime was more than 18 hours. So the null hypothesis is going to be that mu is 18. The alternate hypothesis is that mu is greater than 18. Okay, so she took a sample of 20. So we need to write out her mean distribution. So the mean distribution is going to be L with a hat on it, is normal, still testing for 18, and our standard deviation now is going to be 4 squared over sample size of 20 batteries. Cool. Her test statistic is 19.2. And we're testing at the 5% level. So we're stating my hypotheses. Let's get the calculators ready there. Let's find out what our critical value is, and then we'll compare. So we're looking at distribution, normal, inverse normal. It's greater than, so the tail's to the right. The area is 0.05. Sigma is now going to be 4 over root 20. And mu is going to be 18. So we get our critical value is 19.47. So is 19.2 critical? No. 19.2 is less than 19.47. And you can kind of picture that if I drew a normal distribution. This is my critical value. This is my critical region. 19.2 is here. It's not quite critical. So we say 19.2 is less than 19.47, therefore not critical, therefore accept H1, no evidence to suggest mean life is greater than 18. Mean life is greater than 18. Cool. All right. Ed's asking me a question. Do you think taking account improvement will last first year work based on people who got D last year and retake this year? We've been thinking about that, but obviously the mocks you did were real mocks with first year material in as well. So whatever you got in the mocks was really accounting for that anyway. So maybe very slightly, but it won't be a massive deciding factor. Okay. Right. What are we up to? 15. We got probably time for one more question. Okay, so that's stats done. So that was work through of a whole stats paper. All right, we're going to try this one, and this might bring us up to the end, to be honest. And we'll move on with the rest of this paper next week. Okay, so let's see how you guys do with this one. It's 6 marks. I'm going to give you guys 6 minutes to do it. Starting from now. t is 1 is at the point A, and when t is 4, we want to find the distance between B. Okay. Right. So we need to integrate this to find a equation for our displacement. So S is the integral of t to the minus a half pi minus 4t j dt. And if we do the integral, we're going to get S, or we can call it R, it doesn't really matter. S equals. So t is going to go up to power half, divided by half is 2t squared I. And then t squared divided by 2 minus 2 t squared. I made a mistake there, that should be a half, shouldn't it? I've written 2. Mix up. Sorry, Jasmine. Thank you for telling me. Cool. Yeah, so integrate it to find an expression for our displacement. Okay. Now, normally we'd put plus c. Let's just think about that for a second. C is, if you imagine putting in t equals 0. So let's just say, where does this thing start off? Just as a thought experiment. So if we put in t as 0, we're going to get s equals c. So all we know is that at the initial time, s is at whatever c is. So, but we don't really care about where s starts. All we care about is the distance between point A and point B. So we don't actually need the plus c because we're not finding an equation. We're just trying to find out a distance between 2 points. We're not trying to find out the location of 2 points. We just want to work out what the vector distance is between those 2 points. So I'm going to put in t is 1. So point A is going to be when t is 1. So square root of 1 is 1. So we're going to get 2 in the I direction. And then put 1 in, we're going to get minus 2 in the x direction. Point B, well, I'm going to put 4 in. So we get square root of 4 is 2. 2 times 2 is 4. And then 4 squared, 16 times minus 2 is going to be minus 32. So those are my positions of A and B. Those aren't position vectors, just to be clear, because they're purely relevant to each other. We'd have to find C if we wanted to call them actual position vectors, but they're not. Okay, and we want to find the displacement between them, so we're going to do one take the other, and then find the modulus of it to find the size. So I'm going to do B take A, B minus A. So 4 take 2 is 2, minus 32 minus minus 2 is going to be minus 30. And then the distance is going to be 2 squared plus minus 30 squared, all square rooted, which gives you square root of 904. Is that what it says? Exact distance. Yeah, that's it. Or you could write 2 root 226. But that is it. Cool. Right. What's the next question? Can we get it done in 5 minutes? Hell no. Cool. Right, we'll leave that there for today. So I'm just putting F here to remind me of this is where F group got to. Yeah, right, guys. Well, yeah, if you could fill in that survey online, make sure you're doing the assignments. I'm going to be looking over the weekend to see what's been uploaded so far, and marking anything that I need to mark. And a quick reminder, if you do want your mechanics, if you want me to go through your mechanics tests, drop me a message. Otherwise, I will be emailing out your actual raw marks from the mechanics test over the weekend at some point, whenever I get a chance. Cool. Anybody got any questions on anything we did today? So that's basically your first stats paper that we've gone through. We're going to finish off this mechanics one, and then I think we'll do a pure paper as well. And we'll just keep doing that and working through revising basically. Yeah. Cool. Right, guys. I will speak to you next week. Have a good weekend. Yeah. Bye.